Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into the path to multimodal generalist, general level, and general bench framework. Exciting stuff, right?
Absolutely. I've been following this with great interest. The idea of a general-purpose AI that can handle various tasks and modalities is incredibly appealing. The promise of multimodal learning IT quote S the holy grail, isn't it?
I agree that it's a fascinating area, but I'm also a bit skeptical. The current hype around deep learning and massive datasets, I'm not sure that's the only path forward. I'm wondering if we are missing the forest for the trees here.
I'm with Sarah on this. I think a key point is that current deep learning approaches feel very brute force. The sheer amount of data and computational power they need is frankly insane. I think we need a more elegant, more efficient solution. The framework's emphasis on more data, better results seems simplistic.
Okay, so let's break down the framework itself a bit. It's essentially proposing a standardized way to evaluate and compare multimodal AI systems across a broad range of tasks. The general bench part is the benchmark itself, designed to test an AI's general abilities across different modalities like vision, language, and even maybe robotics down the line. And the general level is, I think, trying to define what capabilities constitute general intelligence. So what are your initial thoughts about that design choice in itself?
I think a standardized benchmark is crucial. We need a way to objectively compare different approaches and track progress. Without a benchmark, it's just a bunch of researchers claiming their AI is better without any real quantifiable evidence. General Bench provides that. It forces us to measure and evaluate.
Yes, the idea of a benchmark is appealing, but I worry about what it actually measures. If it's just testing pattern recognition on a massive dataset, are we really measuring general intelligence or just sophisticated memorization? We also have to look at the possibility of some overfitting of deep learning models on the benchmark itself, which would be detrimental to the whole process.
Exactly. And what constitutes a task? Is it just recognizing images or translating text? What about tasks that require real-world interaction, spatial reasoning, or understanding causality? Current deep learning models struggle with those.
Okay, but hold on. Deep learning has made incredible progress in recent years. Look at the advancements in image recognition, natural language processing, even game playing. These models are learning complex patterns from data without explicit programming. That's a huge step forward. It's not just memorization, it's learning representations of the world.
Right, and that's where the multimodal aspect comes in. The idea is that by training AI on multiple modalities simultaneously, it will learn more robust and generalizable representations. For example, imagine an AI that can see an image of a cat and also read a description of it. By combining these two sources of information, it can develop a richer understanding of what a cat is.
But what kind of understanding is it really? Does it understand the concept of cat, or is it just recognizing patterns in pixels and words? Does it know that cats are mammals, that they hunt mice, that they purr? Current neural networks struggle with that kind of abstract reasoning, you know?
And how does it understand the spatial relationships between the cat and its environment? Can it reason about where the cat might be likely to go next, or how it would interact with different objects? These models treat space as just another set of pixels, not as a structured environment with physical constraints.
Okay, I get your point. Current models aren't perfect, but they're improving rapidly. And the scale of these models is important. The larger the model and the more data it's trained on, the more complex patterns it can learn. It's like building a bigger brain in a way.
But is it really understanding, or is it just getting better at predicting the next word or pixel? AlphaGo was incredible, but did it really understand the game of Go, or was it just a super sophisticated pattern matching machine? There's a difference, you know?
That's a key question, and it gets to the heart of what we mean by intelligence. I think the framework is implicitly assuming that general intelligence will emerge from scaling up current deep learning architectures and training them on massive multimodal data sets. And honestly, I'm not completely convinced. I think we need to look at how the brain actually works, particularly the interplay between neural networks and symbolic reasoning. Maybe we should integrate these approaches more directly.
Exactly. The brain doesn't just process raw sensory data, it also builds abstract models of the world. It understands causality, it reasons about space and time, and it uses language to communicate complex ideas. We need AI architectures that can do all of those things, not just recognize patterns.
But isn't that what these models are already doing to some extent? They're learning representations of the world from data. And as they get larger and more complex, they'll be able to learn more and more sophisticated representations.
But those representations are often opaque and difficult to interpret. We don't really know why a neural network makes a particular decision. It's like a black box. With symbolic AI, you can see the rules and the reasoning process. It's much more transparent and explainable, which makes it easier to trust, really.
Right, and that explainability is crucial, especially if we're going to use these AI systems in critical applications like healthcare or autonomous driving. We need to be able to understand why the AI is making a particular decision so that we can identify and correct any errors or biases. This relates strongly to recent papers that show biases perpetuated in training data are inherited by the neural network.
And let's not forget about efficiency. The energy consumption of these massive deep learning models is enormous. It's simply not sustainable in the long run. We need algorithms that are more energy efficient and that can learn from less data.
Okay, I agree that efficiency is important, but the cost of computation is constantly decreasing. And the benefits of these powerful AI systems outweigh the costs, in my opinion. Think about the potential for AI to solve some of the world's most pressing problems, like climate change, disease, and poverty. We have to continue to push the boundaries of what's possible.
I think a hybrid approach combining the strengths of neural networks and symbolic AI is the most promising path forward. We can use neural networks to learn patterns from data and then use symbolic AI to reason about those patterns and make decisions. Neurosymbolic algorithms, that's the future.
Yes, and there are already some promising examples of this kind of hybrid approach. For example, there are systems that use neural networks to extract entities and relationships from text, and then use symbolic reasoning to answer questions about those entities and relationships. This is far from a solved problem, though.
I think we also need to think more about how to represent space and time in AI systems. Current deep learning models treat space as just a collection of pixels, but space is a structured environment with physical constraints. We need models that can reason about spatial relationships and that can understand how objects move and interact in space and time. We can draw inspiration from spatial temporal databases for some of this.
I'm still optimistic about the path to multimodal generalist framework. I think it's a valuable step in the right direction. But I also agree that we need to be open to exploring alternative approaches, including neurosymbolic AI and more sophisticated ways of representing space and time. The field is constantly evolving, and we need to be willing to adapt and learn.
I think the framework is a good starting point, but it needs to be broadened to include a wider range of approaches. We need to move beyond the hype of deep learning and focus on building AI systems that are truly intelligent, not just good at pattern recognition.
So let's dig a little deeper into some specific research areas that are relevant to this discussion. Otto, you mentioned the impressive progress in image recognition and natural language processing. Can you give us some concrete examples of how these models are being used in real-world applications?
Sure. In image recognition, we're seeing AI systems that can accurately identify objects in images and videos, even in challenging conditions. This is being used in everything from autonomous vehicles to medical diagnosis. For example, there are AI systems that can analyze medical images to detect cancer or other diseases with a high degree of accuracy. And in natural language processing, we're seeing AI systems that can understand and generate human language with remarkable fluency. This is being used in chatbots, machine translation, and even content creation.
But how robust are these systems? How well do they perform when they encounter data that is different from what they were trained on? There have been numerous examples of image recognition systems that are easily fooled by adversarial examples, images that have been subtly modified to cause the system to misclassify them. And natural language processing systems can often struggle with sarcasm, irony, or other forms of figurative language. This fragility is a massive problem.
And how well do these systems generalize to new tasks or environments? Can an AI system that was trained to recognize objects in indoor scenes also recognize objects in outdoor scenes? Can an AI system that was trained to translate English to Spanish also translate English to German? Current deep learning models often struggle with this kind of transfer learning. It goes back to the brute force approach, doesn't it?
Okay, those are valid concerns, but researchers are actively working on addressing those limitations. There's a lot of research being done on adversarial training, which involves training AI systems on adversarial examples to make them more robust. And there's also research being done on transfer learning, which involves developing techniques that allow AI systems to transfer knowledge from one task or environment to another.
Yes, and that's where the neurosymbolic approach can be particularly helpful. By explicitly representing knowledge and reasoning in a symbolic form, we can make AI systems more robust and generalizable. For example, we can build systems that can reason about the relationships between objects and that can use that reasoning to guide their perception and action. In this way, focused pack, we actually understands the concept of what it's seeing. It's not just identifying pixels, but it's a complex problem.
Exactly. And we can also use symbolic AI to make AI systems more explainable. By making the reasoning process transparent, we can understand why the AI is making a particular decision, and we can identify and correct any errors or biases. Neurosymbolic algorithms inherently lend themselves to explainability.
I still think the representation of space and time is crucial. We need to develop models that can reason about spatial relationships and that can understand how objects move and interact in space and time. I've been reading about different coordinate systems and how they're used in physics and engineering. Maybe we can adapt some of those techniques to AI.
That's an interesting idea. So you're thinking about incorporating physical constraints and laws of motion into the AI model.
Exactly. Instead of just treating space as a collection of pixels, we can give the AI a more structured understanding of the environment. This could be particularly useful for tasks like robotics and autonomous driving, where the AI needs to interact with the physical world.
That's a great point, Donald. And it connects to some of the research on embodied AI, which emphasizes the importance of grounding AI systems in physical bodies and environments. The idea is that by interacting with the physical world, AI systems can develop a more intuitive understanding of space, time, and causality.
Yes, and that's also where the neurosymbolic approach can come in handy. We can use symbolic AI to represent the physical constraints and laws of motion, and then use neural networks to learn how to interact with the environment in a way that respects those constraints. We might consider a physics engine being part of the AI model. I wonder if it's possible to get a neural network to learn the constraints on a coordinate system as it's being taught, rather than brute force learning all the possible positions the objects can be in.
Okay, so we're all agreeing that a hybrid approach combining the strengths of deep learning, symbolic AI, and embodied AI is the most promising path forward. But how do we actually build these hybrid systems? What are some of the specific challenges and opportunities?
One of the biggest challenges is integrating the different representations and reasoning mechanisms. Neural networks use distributed representations, while symbolic AI uses discrete representations. How do we bridge that gap? I think this question is especially important when considering neuroplasticity and how the brain's representation of data changes as it learns.
Exactly. And how do we ensure that the different components of the system work together effectively? We don't want the neural network to just be a feature extractor for the symbolic AI. We want the two components to be tightly integrated and to learn from each other.
And how do we handle uncertainty and noise? The real world is messy and unpredictable. We need AI systems that can cope with imperfect data and that can make decisions even when they don't have all the information. This is extremely important when translating between coordinate representations since the data is often quite noisy.
Those are all great questions, and I think the answer lies in developing new learning algorithms that can seamlessly integrate neural networks and symbolic AI. We need algorithms that can learn both from data and from explicit knowledge, and that can reason about uncertainty and noise.
Yes, and we also need to develop new architectures that are specifically designed for hybrid systems. We can't just bolt together existing neural networks and symbolic AI systems. We need to design architectures that are inherently hybrid from the ground up.
I agree. And we need to think more about how to represent knowledge in these hybrid systems. How do we encode facts, rules, and concepts in a way that is both computationally efficient and semantically meaningful? How can we leverage the structure of the brain to inform this?
And we need to develop new ways of evaluating these hybrid systems. We can't just use the same benchmarks that we use for deep learning. We need benchmarks that specifically test the ability of these systems to reason, generalize, and explain their decisions. This ties back into the initial framework.
Okay, so let's talk about some specific research directions that we think are particularly promising. Jesus, you mentioned the interplay between neural networks and symbolic reasoning. Can you elaborate on that?
Sure, I think one promising direction is to develop neural networks that can learn to perform symbolic reasoning. For example, there's research on neural Turing machines, which are neural networks that can read and write to an external memory, effectively allowing them to perform symbolic computations. Another promising direction is to develop symbolic AI systems that can learn from data using neural networks. For example, there's research on inductive logic programming, which is a technique for learning logical rules from data using neural networks. Combining the two could really give us something special.
I'm particularly interested in research on knowledge representation and reasoning. How can we represent knowledge in a way that is both computationally efficient and semantically meaningful? And how can we develop algorithms that can reason about that knowledge in a robust and explainable way? I think ontologies and knowledge graphs are promising avenues to explore. I also think we need to move beyond simple pattern recognition and focus on building systems that can truly understand the world.
I'm excited about the potential of unsupervised learning. Can we develop AI systems that can learn from data without explicit supervision? This would be a huge step towards general intelligence, as it would allow AI systems to learn from the vast amounts of unlabeled data that are available in the world. This also might help us understand and evaluate current neural network performance.
I'm focused on developing models that can reason about space and time. I think this is a crucial capability for AGI, as it would allow AI systems to interact with the physical world in a more intelligent way. I'm exploring different coordinate systems and how they can be used to represent spatial relationships. I also want to investigate how we can incorporate physical constraints and laws of motion into AI models. Furthermore, I would like to understand how to use graph theory to understand spatial relationships between different objects and their different physical representations.
Those are all excellent research directions. And I think it's important to emphasize that this is a very interdisciplinary field. We need researchers from different backgrounds, including neuroscience, computer science, mathematics, and philosophy, to work together to solve these challenges. It's not enough for computer scientists to build AI. They need to understand the underlying principles of intelligence and how the brain actually works.
I agree. And we need to be open to exploring new ideas and approaches. The current focus on deep learning is understandable given its recent successes, but we shouldn't be afraid to challenge the status quo and to look for alternative solutions. I think the deep learning community itself needs to stop viewing symbolic AI as a threat and view it as a tool.
I think the path to multimodal generalist framework is a valuable starting point, but it's just a starting point. We need to continue to refine and improve the framework as we learn more about intelligence and how to build it. We also need to be mindful of the ethical implications of AI and to ensure that these technologies are used for the benefit of humanity.
And we need to be realistic about the challenges ahead. Building AGI is a very difficult problem, and it may take many years, even decades, to achieve. But I believe that it's a worthwhile goal, and that the potential benefits are enormous.
All right, that's all the time we have for today's episode. Thank you, everyone, for joining me on this deep dive into the path to multimodal generalist framework. It's clear that this is a complex and multifaceted area, but with continued research and collaboration, I'm confident that we can make significant progress towards building truly intelligent machines. Remember to subscribe for more episodes where we explore the cutting edge of AI and cognitive science.